In this video presentations, we will talk about polymer flooding concepts. We will discuss the very basics. And let's start with the concept of the mobility ratio or mobility factor. These figures show that when one fluid displaces another in a porous medium, the displacement front or the contact line between these two fluids, immiscible with one another, can be stable, we call it a piston-like displacement, or unstable, with the displacing fluid breaking through the displaced fluid. We call this phenomenon viscous fingering. The figure below shows the same, but in a top view. These are real photos taken from the laboratory, showing one fluid displacing another from a porous medium. And keep in mind that this applies to immiscible fluids like oil and water. In petroleum reservoir engineering, we are dealing with oil displacement by water. So it is obvious that if we inject water into our oil reservoir, we want the displacement front to be stable and more like a piston displacement, because viscous fingering will significantly slow down the oil production rates. We will also be producing a lot of water, while significant volumes of mobile oil will still be present inside the rock. Please note that in the piston-like displacement case, the volume which was flooded by water has no mobile oil left in it. There is some oil left in this volume, but it cannot be displaced by regular water flooding. Pretty much in the same way, you cannot wash out 100% of oil from your t-shirt if it has been soaked in oil. Cold or even hot water will wash out a significant volume of that oil from your t-shirt, but tiny oil droplets will be left inside some tiny fabric pores, from where water cannot remove them. You would have to use soap in order to wash this oil out, or some kind of solvent to clean the fabric from the residual oil. But right now we focus on mobile oil, which makes up around 65–70% of the total oil present inside the reservoir. And as I said, in the piston-like displacement mode, the volume which was flooded by water contains no mobile oil left. There is no more oil left for the water to displace in this part of the reservoir. However, if our reservoir conditions are such that piston-like displacement is not possible, and we are dealing with unstable displacement with a lot of viscous fingering, the portion of the reservoir that has been flooded by water still contains a lot of mobile oil present in between the fingers of water. And of course, this mobile oil will be displaced as we inject more water and the displacement front propagates through the reservoir. However, the volume of water we must inject in order to displace all mobile oil from this reservoir is much greater than the volume of mobile oil itself, whereas in a piston-like displacement reservoir, 1 barrel of injected water displaces 1 barrel of mobile oil, and water will start exiting the reservoir from the production well side only after no mobile oil is left. So it is obvious that in reservoirs where the conditions favor piston-like displacement of oil by water, the economy of water flooding is much better. At this point, let's figure out which conditions determine whether we are dealing with piston-like displacement or unstable viscous fingering displacement. Intuitively, you can say that if the velocity of water is equal to or less than the velocity of oil, then water will not tend to break through the oil bank. And if the velocity of water is greater than that of the oil, then water will tend to break through the oil bank by forming viscous fingers. And keep in mind that for simplicity, we're thinking of a homogeneous one-layer reservoir. So there are no fractures or high permeability layers that can act as channels for the water to bypass oil. In this particular case, the only issue that slows down the production of mobile oil is the mobility difference between water and oil. We want the mobility of water to be equal to or less than that of oil. And which reservoir conditions determine or affect the mobility or the velocity of water and oil? Of course, from Darcy's law, we know that the velocity of a fluid inside porous media depends not only on the pressure gradient, but also on the viscosity of this fluid and permeability of the porous media to that fluid. So using Darcy's law, we can write down the ratio between the velocity or mobility of water and oil inside a porous medium. This ratio is called mobility factor, one of the fundamental concepts in reservoir engineering. It characterizes the process of oil displacement by water. If the mobility ratio is greater than unity, this means water is faster than oil and will tend to break through the oil bank. From the formula of the mobility ratio, we see that high permeability to water and high oil viscosity will cause the mobility ratio to be high. This makes sense because high permeability to water allows it to move faster, and high oil viscosity prevents it from moving fast inside porous media. So we already understand that in order to facilitate the displacement of mobile oil, we have to reduce the mobility ratio. This can be practically done by increasing the viscosity of water through the addition of high molecular weight polymers. And in this one-layer reservoir, the decrease of the mobility ratio from some high value determined by the initial reservoir conditions will facilitate mobile oil displacement. Decreasing the mobility ratio to unity will be enough to achieve a stable displacement front in this one-layer reservoir.